In today's video, we will learn how to find the moment of inertia of composite section with cutout holes. The figure shows a composite section which consists of a triangular section, a semicircular section and a circular section. And from the figure, it is also clear that we are removing the circular section from the composite section. Now, the axis about which we need to find the moment of inertia is also given in the question, which is marked as capital AB. Now let's see how to find out the moment of inertia, or what are the steps involved in finding out the moment of inertia of the composite section. So as I have told earlier, the composite section can be considered as a combination of a triangular section, a semicircular section and a circular section. So I have drawn the axis about which we need to find the moment of inertia, which is marked as capital AB, and then I have numbered the symbol figures as 1, 2 and 3. 1 denotes the triangular section, 2 denotes the semicircular section and 3 denotes the circular section. Now the next step is to find the moment of inertia of the triangular section about the axis AB. So we can see from the figure that AB is the axis which is passing through the base of the triangular section, and we have already learned the formula for finding out the moment of inertia. When you consider the semicircular section, again you can see that the axis is passing through the flat end of the semicircular section. And when you consider the circular section, you can see that the axis is passing through the CG of the circular section. We have already learned the formula for finding out the moment of inertia of these three symbol figures. Then once we found out the moment of inertia of the triangular section about AB, semicircular section about AB and circular section about AB, we can find the moment of inertia of the composite section using the formula IAB is equal to IAB1 plus IAB2 minus IAB3. Why minus IAB3? Because we are removing the circular section from the composite section. Now let us take one by one. The first one is triangular section. So we know the moment of inertia of a triangular section about an axis passing through the base, that is, which is denoted by IAB1 is equal to BH cube by 12. So that will be equal to 80 into 80 cube by 12, which is equal to 3.413 into 10 raised to 6 mm raised to 4. Now the second one is semicircular section. So in the case of semicircular section, the moment of inertia about an axis passing through the flat end of the semicircular section is given by pi d raised to 4 by 128. So in our case, IAB2, that is moment of inertia of the semicircular section about the axis AB, will be equal to pi into 80 raised to 4 by 128, which is equal to 1.005 into 10 raised to 6 mm raised to 4. And the third one is circular section. So here we can see that the axis is passing through the CG of the circular section. So the moment of inertia of the circular section about an axis passing through its own centroid is equal to pi d raised to 4 by 64, which is equal to pi into 80 raised to 4 by 64, which is equal to 0.126 into 10 raised to 6 mm raised to 4. Now the moment of inertia of the total area or the shaded area IAB about the axis AB will be equal to 3.413 into 10 raised to 6 plus 1.005 into 10 raised to 6 minus 0.126 into 10 raised to 6, which is equal to 4.29 into 10 raised to 6 mm raised to 4. Now let's take the second question. So here we need to find the moment of inertia of the section about a horizontal axis passing through the centroid of the composite section. Now here in this figure you can see there is a rectangular section as well as a circular section, and we are removing the circular section from the rectangular section. Now we need to draw the horizontal axis passing through the centroid. So the first step is to locate the centroid of the composite section. So for that we will draw the composite section first. Then in order to locate the centroid, we assume an axis passing through the base of the rectangular section, which is marked as capital XX. Then when you draw a vertical line passing through the center of the rectangular section, you can see that the section is symmetrical, which means the CG of the figure lies anywhere on this line. So let us assume that capital G is the centroid of the composite section, which lies somewhere here, which is at a distance of y bar from the reference XX axis. Now in order to locate the centroid, we will divide this composite section into two symbol figures The first one is the rectangular section and the second one is a circular section. Now using the formula, y bar is equal to a1 y1 plus a2 y2 divided by a1 plus a2, which is equal to sigma ai yi by sigma ai. We can find out the distance of G from the reference axis. Now the table here consists of 5 columns. The first column denotes the serial number, second column denotes the shape of the symbol figures, third column denotes the area of the symbol figures, fourth one shows the distance of CG of symbol figures from the reference x axis, and the last column shows the product of AI and YI. Now let us take one by one. The first one is a rectangular section. So area of the section will be 200 into 300, which is equal to 60,000. Distance of CG of the rectangular section will be at a distance of 150 mm from the base of the rectangle, and AI YI will be equal to 60,000 into 150, which is equal to 900,000. Now the second one is the circular section. So we know that we are removing the circular section from the composite section. So we will provide a negative sign in the area. So area will be minus pi r square, which is equal to minus pi into 75 into 75, which is equal to minus 17671.46. So what is y2? Y2 is the distance of centroid of the circular section from the base. So that will be equal to 300 minus 100, which is equal to 200 mm. And AI YI will be minus 17671.46 into 200, which is equal to minus 3534291.73. Now let us find the algebraic sum of all the areas, and we can write that here. So sigma AI will be equal to 42,328.54 mm square, and we need to find the algebraic sum of AI YI also. That will be 5465708.27. Now in order to find y bar, final value divided by the sigma AI value, which will be equal to 129.13 mm from x axis. Now let us try to find the moment of inertia of the rectangular section about the centroidal x axis shown in figure, and moment of inertia of the circular section about the reference x axis passing through the centroid of the composite section. In order to find the moment of inertia of the rectangular section, let us first remove the circular section from the composite section. Now how will you find out the moment of inertia of the rectangular section about the centroidal x axis? So that can be found out using the parallaxis theorem. So for that we need to locate the centroid of the rectangular section first. So G1 is the centroid of the rectangular section, which will be exactly at the center of the rectangle. Now, if we know the moment of inertia of the rectangular section about its own centroidal x axis, we can find out the moment of inertia of the rectangular section with respect to any other axis parallel to the centroidal G1 x1 axis. So that can be done using parallaxis theorem. Okay, now what is parallaxis theorem? Ixx1, moment of inertia of the rectangular section about x axis. What is Igx1? It is the moment of inertia of the rectangular section about its own centroidal x axis. A1 is the area of the rectangular section, and what is h1? H1 is the distance between the centroidal G1 x1 axis and the axis about which we need to find out the moment of inertia, that is centroidal x axis. So this distance, that is the distance between these two axes, is h1. Now how will you find out this distance? H1. So we know that the centroid of the rectangular section will be at a distance of 150 mm from the base of the rectangle, and we know this distance also, right? That is y bar is equal to 129.13. So h1 will be equal to 150 minus 129.13. What is Igx1? Which will be equal to 200 into 300 cube by 12, which is equal to 4.5 into 10 raised to 8 mm raised to 4. Then A1 is B into D, which is equal to 200 into 300, which is equal to 60,000 mm square, and H1 is equal to 20.87 mm. Therefore, Ixx1 is equal to 4.5 into 10 raised to 8 plus 60,000 into 20.89 square, which is equal to 4.76 into 10 raised to 8 mm raised to 4. Now let us take the circular section. Now in order to find the moment of inertia of the circular section with respect to x axis, we can apply the parallaxis theorem. That is Ixx2 is equal to Igx2 plus A2 into S2 square. What is Igx2? Igx2 is the moment of inertia of the circular section with respect to its own centroidal x-axis. So we need to locate the centroid of the circular section, which is denoted by G2 in the figure. So G2 x2 denotes the axis passing through the CG of the circular section. So if we know the moment of inertia of the circular section with respect to G2 x2, we can find out Ix x2 also. So what is Ig x2? Ig x2 is equal to pi d raised to 4 by 64 that we have already learned, which is equal to pi into 150 raised to 4 by 64, which is equal to 0.249 into 10 raised to 8 mm raised to 4. Now A2 is the area of the circular section, so which will be equal to pi into 75 into 75, which is equal to 176 71.46 mm square. Now what is H2? H2 is the distance between G2 x2 and the axis about which we need to find the moment of inertia of the circular section, that is x axis. So H2 can be found out by subtracting 100 from 170.87. That means H2 will be equal to this distance 170.87 minus this distance, right? That is 100. That will be equal to 70.87 mm. So Ixx2 is equal to 0.249 into 10 raised to 8 plus 17,671.46 into 70.87 square, that is equal to 1.14 into 10 raised to 8 mm raised to 4. Now we have Ixx1 and Ixx2. So to find out the moment of inertia of the composite section, we can use the formula Ixx is equal to Ixx1 minus Ixx2. And why we are using minus Ixx2? Why we are putting negative sign for Ixx2? That is because we are subtracting the circular section from the rectangular section. So that will be equal to 4.76 into 10 raised to 8 minus 1.14 into 10 raised to 8, which is equal to 3.62 into 10 raised to 8 mm raised to 4.